Good afternoon, everybody. Thank you guys for being here. Those that are here present today. Thank you for those that are connected online. It's actually my first time in this in auditorio format. I came back from Brazil last week, so it's really a pleasure to be here and see how it works in person. And today is a very special occasion because we have also our first in-person speaker today, and this is a big name in quantum physics. This is Professor Markus Aspelmeyer from the Vienna Center for Quantum Science and Technology, and also the Faculty of Physics in the University of Vienna, and Institute of Quantum Optics and Quantum Information, right? Professor Markus Aspelmeyer is, like I said, is a big name in our field. Everybody read papers of his in his PhD, and it's really a pleasure to have him here. It's difficult to fall short with it's easy to fall short with the introduction because he has done so many things. He's really an authority in anything that has to do with micro and nanomechanical quantum systems. He did actually a bachelor. He has a bachelor in philosophy. After which he got a PhD in physics from the University of Vienna, also with Professor Anton Zeilinger, who's also a big name in our field. He then was a researcher in ICOQ, the Institute of Quantum Optics and Quantum Information. He won several different prizes, Lieben Prize in 2007, different ERC grants, starting consolidator. He has also a huge Synergia projects also. He won the Fresnel Prize from the European Physics Society, Ignaz Lieben Prize from the Austrian Academy of Science, Fritz Kohlrausch Prize, Austrian Physical Society. He even co-founded a startup, Crystalline Mirror Solutions, that was later bought by Thor Labs, by which he also won some innovation prize also, and the list goes on, and it's very long, right? So the most important thing is that it's really a pleasure to have a scientist of such high level of science quality, right? It's really a pleasure to have you here, Professor Aspelmeyer. Thank you for coming. Thank you for being here, and yeah, proceed. Thank you.
Thanks a lot, Leandro. I'm super happy to be here. Thanks for the invitation. And after this introduction, I can only make it worse. So maybe I should just stop and ask for questions. So, well, you can see the title, and what I would like to do is it's really more like a tour de force through different topics that have been part of my interest and are now my interest at the moment. And yeah, you will see what it is about, okay? So I leave the title just as it is. Let me briefly, for the introduction, say one of the nice things about being in Vienna is that in my case, I basically sit right next to the library that hosts the Schrödinger archive. So it means you can go there in the evening and you can browse through the letters that Schrödinger sent and received, sometimes even the originals. And I would like to share with you one letter that I found recently that was written by Einstein when he was already in the States. So it starts, Dear Schrödinger, lieber Schrödinger, you are in fact the only human with whom I really like to discuss. Almost all the guys do not see the theory from the facts, but only from the theory the facts. They cannot get out of the concept net once assumed, but only fidget around in it. But you look at it as you wish, from the outside and from the inside. Although in the way that in the way to expect, we are the strongest antipodes. This is the end of the abstract. So, and the way what to expect was really about the foundations of quantum physics, was about the question, what does the wave function refer to? What does physics, quantum physics, say about nature? So essentially the deepest philosophical questions. And the discussion between the two, that was part of that letter, culminates in the famous thought experiment of Schrodinger's cat that many of you very well know. So this is a quantum optical version. So what is this about? Essentially, quantum physics tells you that there are experiments, or it allows for experiments, whose outcomes, the experimental outcomes, are inconsistent with the assumption that either one or another situation was the case. Now, for example, the location of a photon behind a beam splitter. So in quantum physics, we say, oh, there's a superposition. Okay? We loosely say it took both places. But what we actually mean is that we have an experimental outcome that is inconsistent with the very assumption that the photon either took that way or that way. And if you couple that now to some evil device, Schrödinger's words, then you end up in a situation where you have exactly this so-called superposition that contains a state of the cat where the cat is doing well and doing not so well. And what that means is that in principle we could perform an experiment whose outcome is inconsistent with the assumption that the cat was either alive or dead. Yeah? And Einstein was definitely not happy with that situation, and this is also a quote from the letter where he explicitly said, you see, my problem with that is that by no art of interpretation can this psi function that describes this state in nature be made an adequate description of the real factual situation. Because, he goes on in the letter, because in reality there is no such thing as a cat being both alive and dead. Nevertheless, we will see that later, do have experiments that show that these predictions of quantum physics are correct. Nature allows for such states that are inconsistent with the assumption that either one explicit or another explicit situation is there. Yeah. Done. Okay? This was quantum physics. What about the other theories we know about? What about gravity? Okay. Well, the best known theory of gravity is Einstein's general theory of relativity to describe phenomena of gravitation. And what do we know today? Well, there's not really a force. Instead of talking about a force, we say that we have motion in a curved space-time. So large masses bend space and time, affect the metric of space-time, and smaller test masses move along geodesics in this curved space-time, and we perceive that as a force between these two objects. This is our current notion of gravity. Done that. So here are two statements of facts. Statement number one, quantum theory works. Here is a beautiful experimental example from my colleague Markus Aspelmeyer in Vienna, who holds the world record in preparing quantum superpositions of massive particles, macromolecules. You see, these are molecules that contain thousands, hundreds of atoms, more than 1,000 atomic mass units, and we can prepare them in such superposition states. We can perform experiments, the outcome of which is inconsistent with the assumption the molecule was either here or there. It was delocalized. It's in a superposition state, and as a result, he sees these extremely beautiful quantum interference fringes that cannot be explained by a particle that is just at a specific location in space. On the other hand, we know also general relativity works. This example you also know. This was the famous recent discovery of gravitational waves by these large-scale laser interferometric gravitational wave observatories in the US, and now also seen in Europe and being built up all around the world. So this is our current state of the situation of the two most powerful theories about nature. I sum up one more time. Quantum theory works, as does GR, general relativity. So to this day, there is no experiment that would contradict the prediction of either of these two theories. Okay? So you can ask, well, so where's the problem? We should be happy that we have such powerful theories to describe things on the large and the small scale. So the real problem is that these two theories rest on completely orthogonal worldviews. Okay? they're essentially mutually exclusive. So gravitational theory, GR, does not know about the superposition principle, about complementarity, and so on. Okay? Just cannot handle the concept, their whole idea. On the other hand, quantum theory cannot work, cannot live with a situation where a specific thing like the metric, the space-time metric, is fixed for all times. So basically is observer independent, if you want. Okay? So in other words, if quantum theory is correct, somehow we must radically rethink our notion of space and time. There's no way around that. And on the other hand, if GR is fundamentally on all levels correct, we somehow must radically rethink the role of quantum theory in our description of nature. There is this tension. At the end of the day, this is an experimental problem. I'm sorry, I apologize to all the theorists here. But, and it's an experimental problem in the sense that right now there doesn't exist a single experiment that would actually answer the question whether gravity requires a quantum description. We do have many theories that tell us how a quantum theory of gravity could look like, but we do not know if nature actually requires a quantum description of nature. And this is the actual challenge. Can we come up with such experiments? So what we do know very well, and there are beautiful experiments, is how quantum physics reacts to gravity. So we can have quantum systems as test masses in external gravitational fields, for example. I give you two of my most favorite examples. There are many, many more. This would be a separate talk, actually, to introduce you to all this beautiful physics here. So here are two examples how quantum systems react to gravity. In this case here, this is the famous experiment by Colella, Overhauser, and Werner, also called the cow experiment, after the initials of the authors, that probes the influence of Earth's gravitational field on the wave packet of a neutron. So the main idea is when I have a particle that traverses through an external potential, doesn't matter if electric, gravitational, and so on, it accumulates a dynamical phase. But we cannot measure global phases, we can only measure phase differences. So what we do is we build an interferometer where we split the neutron wave packet in two. So there's a single crystal where the neutron wave packet is just diffracted. Oops, sorry. Where the neutron wave packet is diffracted, and then it goes along two paths. And if you rotate now this interferometer in Earth's gravitational field, you see that the two paths see two different gravitational potentials, and you accumulate a phase difference along these two paths. And so you can re-interfere them and then measure this phase difference. And you get, dependent on the phase angle, which means a difference in the height of the two paths, you get an interference pattern induced by Earth's gravitational field. The other beautiful example is by the group of Dave Wineland at NIST, who showed the gravitational time dilation, the gravitational redshift on an optical clock. So what you see here, I don't know if the picture, it's not really good enough, but what they have is they have an optical clock setup. So it's a large optical table with an optical clock built on it, and they measure the frequency of this clock. And then they lift the whole optical table by 30 centimeters in Earth's gravitational field. Yeah, and what you see is, whoop, the frequency changes. Yeah, so you have a sensitivity of a quantum system of the frequency with respect to the location of Earth's gravitational field. And if you looked at the archive recently, a couple of weeks ago, there was a fantastic paper by Juni's group at Chile who demonstrated a gravitational effect over a millimeter spread in an atomic cloud. This is the precision right now that we have with which we can measure gravitational effects of Earth's gravitational field using quantum systems. Okay? So this we understand very well, and also the theory is very well developed. So in the, let's say, the best theory at the end is then something like quantum field theory in a curved spacetime. So the mass, Earth, for example, generates the metric. And now in this non-Minkowski metric, we then have to write down our quantum field theory to describe the experiment. This is like the most advanced way of describing that. Okay? So this answers the question, how do quantum systems react to gravity? Okay? Now, what about the other way around? How does gravity react to quantum systems. What's gravity's reaction? And this is a question that, if you look in the literature, this dates back at least, well, of course, there are many theory works already in the very beginning of gravity theory. So already in the 20s, you find papers about questions of the interface of quantum physics and gravity. But the way that I'm looking now is has been first discussed around in the 50s by Feynman and others at the now famous Chapel Hill conference. This was a conference that was organized by the de Witts on the role of gravity in physics, because it was believed in the early 50s that gravity research is done. There's nothing interesting anymore to discover. All is known, and there shouldn't be any papers anymore on gravitation, because what could you publish new? And actually, Wheeler and de Witts wanted to make the case that there's still many more things to discover, and they organized this conference. They brought together like the experts in gravity and field theory at the time. This was worldwide, maybe 30, 40 people, and they met at Chapel Hill, and Feynman was among them. And there, one of the discussions was, does gravity require quantum description? This was one of the big questions that was discussed. The other big question that was discussed at the meeting was, do gravitational waves exist? And it was at this meeting that basically also the theoretical, let's say, foundations were solidified, I would say, with Brill and others, and of course then laid also the foundation for the experiments. Okay, so here's the idea. What about designing an experiment, I use now Feynman's word, which uses a gravitational link and shows quantum interference? What does he mean? He means, well, what about we now don't use a quantum system as a test mass in an external gravitational field, but what about if we use the quantum system as a mass that generates a gravitational field? What's the consequence? How does the gravitational field of a quantum system actually look like? And the type of experiment that he proposed was inspired by a Stern-Gerlach experiment. So let's assume you have some sort of particle beam, and you have a Stern-Gerlach device that places this particle now in a superposition of being up there and there. Yeah? And then you take a second object that gravitationally couples now to this mass in a superposition. Okay? What happens? Well, nowadays we are all in the end we are all quantum physicists by now. No, we learn it in kindergarten, so we can all write down the start here. So we start out with this superposition. Our mass is source mass is either up or down, okay, and our test mass is away from it. And now we have gravitational coupling. So that means you see, each of these two branches generates an acceleration, because the source mass, what does the source mass do? It bends space-time. So that means the test mass is now accelerated, and the acceleration depends on the distance between the two masses. So that means that this branch here will have a different acceleration than the other branch, which means over a certain amount of time it evolves into an entangled system. There's now correlation in position, and it's actually a superposition. It's a superposition of correlations between the possible positions of the source mass and the test mass. It's an entangled state. Okay. Now you see, from a quantum physics point of view, this is super trivial. Now, of course, they get entangled. I have a superposition here. I couple to a distant particle via 1 over r potential, and I get entanglement. So I should not be surprised. From a GR perspective, it's interesting. I just told you how we think about gravity. What gravity does is source mass generates a metric within which we have chair-desic motion of the test mass. Now, if the metric that my source mass generates would be just a fixed spacetime metric, then any test mass would just move along the geodesic of this fixed spacetime metric and would never be able to become entangled. If they are separable, these two systems, at time t equals 0, they will be separable at all times, because the test mass will just move along one trajectory. Okay? It will be at a different position, but there will be never any entanglement. So entanglement requires that the metric within which I have my geodesic motion for the test mass is in a superposition. And this is the interesting part about that. If I would be able to do such an experiment with a source mass in a superposition, and if I would be able to entangle these two systems with each other, then I would have an experiment that shows that gravity requires a quantum description. I at least have to assume that my metric is in a superposition. I cannot say anything about field quantization, gravitons, blah, blah, blah. But I don't have to. What I'm interested in is, does gravity require that I have to apply the principles of quantum physics to its fundamental properties? Okay, so this is the, and so this would be the really fascinating outcome. I'd say this is not a question. Go ahead, René. The mic.
So can you say if there's an issue with this? So it sounds like there's an issue, right? Let's say you would like to have this, you would like to have your space-time metric in a superposition. It's not obvious how you do this. You could not just write it in a superposition. Or what is the issue with this? Yeah,
okay,
I don't know. Yeah.
So there are two issues. The one is, so you're talking about two issues. So there are two possible meanings of issues. The one is the experimental issue, and I'm going to talk about this. There's definitely an issue. And the other one, from a theory perspective, the question is, well, do we actually have a theory to describe that? And there the answer is, well, yes. In principle, we do, because from a quantum perspective, also from a GR perspective, we are talking about a tabletop experiment. So we are talking about a regime in which I do not need to apply the full power of Einstein's field equations. I can linearize this whole thing. I operate in the regime where I have effectively a Newtonian interaction, still retarded. So it's still a gravitational field. So there's no instantaneous interaction. But I operate in a regime where I have a linear field theory, and for that, I claim that this is a homework problem in my quantum field theory class, that I can write down an effective field theory. Effective quantum field theory for this linearized regime. And I also would expect that any quantum field theory of gravity would, in the low energy regime, sort of end up in this Newtonian limit where the superposition principle applies. So I would expect this sort of consistency.
But isn't there a problem that, I mean, in the linearized regime, you end up with a scalar field. So, I mean, you cannot, like, renormalize it. Like, I mean, there's no consistent quantum theory of scalar fields.
This I don't know. Okay. This I leave to the people who have done string string theory in the past. Yeah.
So I mean, you can handle with cutoff, but I mean, it's unpleasant.
Yeah.
Theoretically.
Yeah. So probably, what I'm referring to, there are works from the 80s. I need to get up, but there are a couple of papers where people write down an effective quantum field theory for gravity, and I assume that in these specific papers they are working with cutoffs, that is somehow then legitimate. Yeah. Thanks.
So, just to be sure I'm in the right direction. So I don't see any issue, strictly speaking, because the thing is that you did not define what you mean by entangled metric. Right, this is the thing. Am I correct? So once you define some kind of some metric being in a superposition state, then I mean we can understand whether there is an issue or not. Right? Again?
Yeah.
Shall
again.
Shall
yes.
I?
Again.
Okay. Say I don't see, strictly speaking, any issue.
From a theory point of view.
From a theory point of view, because what I see is that you did not define what an entanglement matrix is, right? So once I see this definition, then we can discussing.
Yeah.
I also think that the nonlinear part is essential because gravity is nonlinear, right? So I don't know what I would be talking about, but I think nonlinearity is important, right? Okay.
Thanks. So definitely, if you want to write down a full quantum theory of gravity, nonlinearity is important. what we were discussing now in response to René's question was, what do we expect for these type of experiments? For these type of experiments, the nonlinear contribution is essentially non-existent, so it's not relevant. And my statement is that still, even though this strictly works in a linear regime, the outcome for such an experiment is relevant because it provides you with an answer if at all the underlying principles of quantum physics can be applied to gravity. If it can be applied in the linear regime, well then at least we have a phenomenological legitimization to work on full nonlinear quantum theories of gravity. Mm-hmm.
Could you tell us what are the quantities which I have to compare to see if I can linearize or not? So if I look at the equations, so which normally, right, I can say this quantity is now much smaller than this quantity, therefore I can linearize.
Mm-hmm.
So what would this be in this context, or is this a hard question? Depends on the experiment.
No, not really, exactly. So it's basically what you.
Is the curvature, right?
It's the curvature. You write down and it's also the non-relativistic. In the end, it's the energy momentum tensor, right? So it's the two mu components. Where the question is how large are they, and basically it's if only the mass density component, so the 0,0 component remains, then it's sort of the low energy non-relativistic regime.
So this is very interesting, but I suggest that we let the speaker go on, and perhaps because there will be many more interesting questions, I think.
Yeah,
Thank you.
but it's definitely a crucial
Thanks.
crucial part,
Crucial
right?
point.
So
Yeah.
okay, so which brings me now to the experimental question, right? Namely, so can we think now of quantum systems as gravitational source masses? Or to put it, actually, Witten, Louis Witten, the father of Ed Witten, was also present at Chapel Hill. And when Feynman presented that Gedanken experiment, he actually stood up and said, what prevents this from becoming a practical experiment? And that is basically the question that I now would like to ask. So can we do that or not? If you would have asked me 15 years ago, I would have said no way. But it turns out the developments over the last 10 years, now maybe even 15 years, made me believe that I claim at least I know how to do it in principle. If it will be doable in practice is a completely different question. But just the sheer fact that we have an in principle roadmap is already, well, for me it's enough. And I'm very excited about that. So here are the two questions that we need to address when we want to take that seriously. Number one is, how small can I actually make a gravitational source and still measure its gravitational field? So because I need, in order to make such an experiment happen, I need to isolate gravity as a coupling force for super small objects. Okay? So question is, what is this experimentally feasible? Where are the technological limits in the measurement, in the isolation, not only measurement, but isolation of small gravitational forces? And then the second question is the second part then of the talk, starting from a quantum system, how massive can we make it? Yeah, so the one is like a top-down approach. Start with gravity of Earth, how small can we make it and still measure something? And the other one is a bottom-up approach. Start with an atom in a quantum state and how many atoms can we add and still maintain its quantum nature. Okay? So here's a quick reality check, and I just want you to focus on the right side here for a second, namely, so this is mass on the x-axis, coherence time on the y-axis, and I first want to talk about the gravity part, okay? So the question is now, how small can we make a source mass? So, and what's the smallest gravitational field that we can actually measure? So if you look in the literature, like half a year ago still, the smallest source mass that people have measured a gravitational field of was in the order of a gram. Okay, and our question was, well, how can we push this here much more to the left? And this is right now. This is a research in progress. I give you the rough idea. Okay? And since he told me there are also non-experts, I made a little animation for you. So what you can see here is we start with a gold mass, okay? Then we take a second gold mass and we periodically modulate this mass, which is the source mass, and therefore I create a time-dependent gravitational acceleration on the location of the test mass that will follow. So in the end, that's basically a Cavendish type experiment, but just with very, very small masses. That's trivial, yes?
The previous slide,
Wait.
I can repeat the question also.
So in the previous slide, the first reference is 88. The
Yes.
second one's 2020. There's a 30-year gap. Why?
Because there was no motivation to measure gravity for small masses. So the reason why it was measured in 88 was people were interested in how a gravitational law behaves at small distances. Okay? So there are also coming from string theory, there are some conjectured consequences of such high energy theories, even at low energy again. And one of the consequences is that Newton's, so the gravitational law, the 1/r² force law, should be modified at small distances. So this is why people started looking at small distances. And of course, how do I get small distances? I need to make the object small, because with a large object I can only approach it, so the diameter is the limit. And so people made small masses. So these were the experiments by Mitrofanov. And then, starting from the 90s, or even back in the 80s, there's an incredible bulk of literature and amazing, really, I mean, these are mind-boggling experiments by the Edelberger group from the University of Washington, the so-called Earthwash group, who just perfectioned gravity experiments, and also making the masses smaller and smaller. And it was only here, see, what is it, 2020, right, that they also then operated in a mass regime that was similar to Mitrofanov. A difference, Mitrofanov had spheres, and this was limiting the distance, and what Edelberger did was he made disks that he approached. Okay, so he could keep the masses larger and make the distance smaller. Okay, and only because of some technical reasons they went then to smaller masses back then in 2020. This the long story for the reason. Sorry for this long. Okay, so here is the, I can now make a shortcut. I already showed you what the idea is. Just one more time. So you modulate here the position of the source mass, which means you modulate the gravitational field, and therefore the gravitational acceleration that the test mass is experiencing. Yeah? And what we did was here the test mass is essentially part of a torsional oscillator, torsional pendulum with a few millihertz resonance frequency. The drive happened at some 10 millihertz, and you see that with the parameters that we have a mass on the order a millimeter gold sphere, a 90 milligram source mass. We have the closest distance between the surfaces is down to 400 micrometer between the two, and the acceleration that the test mass is experiencing is on the order of 10 to the minus 11 g. So that means when we modulate the source mass by a few millimeter, the test mass is displaced by a few nanometers, and this is what we need to measure. Okay? We need to measure a periodic response of the test mass on the nanometer regime, and also because we modulate the whole thing in a 1/r potential, not only do we have a linear response of the test mass, but also higher order responses. So we even see double frequency response or higher order generation in response of the test mass. Luigi.
Yes, can you comment a little bit? So I lost, it's my problem. So there's a Faraday shield. So
Yes.
The role of the Faraday shield.
Okay, so if you noticed in my talk title, and I will never be able to come to that point in my talk, but that's okay. In my talk title, I talked about levitation. The reason why levitation is so nice is because when you levitate an object, you can remove all the charges on it. Here you see this is an experiment still very classical where the torsional balance is hung on a silica fiber Even though everything is gold coated and we even use LIGO technology, so we have ionized gas that we have passed through the chamber to get rid of charges, we still have on the order of 10 to the 3 charges on top of the masses. Because this whole thing is connected to the outside world and not levitated, there's no way to remove all the charges. So that means if we don't have the shield and we modulate the source mass, we also see a super response of the test mass, which is due to charges. Okay, it's not Coulomb, by the way, because the charges redistribute; they are freely floating, and it's not a 1 over r square Coulomb law. It's a beautiful theory, by the way. Lechner has done that already, and we have confirmed that now for these masses. But with the shield, we basically shield the effects. We still have then an offset, but it's DC. So basically, when you modulate now the mass, you don't see any charge effect anymore on the test mass.
How do you move the source mass? How do you make sure that everything? How do you move the source mass? How do you make sure everything you detect is not basically an error of a tiny motion of the source mass? Do you understand my question?
Yes. So the source mass you see is on a titanium rod. Now I can later show you some more details also if you want. It's on a titanium rod that is mounted after a long distance on a bending piezo. So the bending piezo actually bends and then displaces the titanium rod, and that does a movement like that. Okay, and so what we did, of course, was we also let the bending piezo operate without the source mass. Okay, so because if you move now, then you have momentum transfer on your chamber. Right? So it could be that what we see is not a gravitational effect, but it's just a momentum kick due to the motion of the rest of the machinery. So we did a very elaborate systematic analysis of all these other possible effects, and this we could exclude, for example, by this method. You also have to exclude magnetic effects, okay, and so on and so on. Good. But so just to show you also here the type of other sources of errors that we have. So this is now, you see, this is time, and here's frequency, and the color coding is the strength of the response of our pendulum. So yellowish means a strong response of the pendulum, and bluish means nothing. Okay, so that means now here, let's say at a certain point in time, you see you have these stripes in here, which means there's a resonance. Okay, and then there are higher orders, multiples of this reference. Okay, so resonance. So there's a here 10 to the minus 2 is the fundamental resonance of the pendulum. Da 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 da. Okay, and you see that apart, except from these blue stripes here, they are always excited. So we see a strong excitation of the pendulum here, and it turns out that what we see here, this excitation, this coincides with the traffic light cycle at the road crossing that is 60 meters away from our lab, a Vienna basement lab, okay? And at the road crossing, there are trams accelerating, decelerating, there are cars accelerating, decelerating, there are pedestrians crossing, and this is this resonance here coincides nicely with this traffic light cycle. Say again?
The tram is in time, always. Traffic light is.
So since you are asking, so this is the noise spectrum, okay, over time, and this is during the day, and then comes night. You see, at night it becomes more quiet, okay, and you see this thing here, that's the night bus, and it's always in time apart from here. You see, here it's late. This is a late night bus. That's the most expensive traffic monitoring system they have in Vienna. Yeah.
How does it couple? Gravitationally or?
No, this is seismic coupling. This is seismic coupling. So if you put the numbers, the amazing thing is that I now know the weight of a Vienna city tram. It's 90 tons, 90. Okay, and I know that because the gravitational pull of a 90-ton tram that is 70 meters away from our lab is the same order of magnitude than the gravitational pull of a 1 millimeter gold mass sitting a millimeter away from your experiment. So it's, and the only reason why we survive here is because we have this torsional pendulum and we are sensitive to the field gradient, to the force. And the nice thing is, because it's so far away, the size of our experiment is too small to pick up the field gradient. But in principle, this is a distraction. Yeah, definitely. Okay. Well, and then of course you can guess now the blue ones are, of course, this is the night. The blue lines is the night when the trams don't go anymore in the cars. Yeah. And even there you can distinguish 5 dark lines and 2 less dark lines, which is Friday and Saturday night when people are out in the street. And so these are the dark ones are of course the best times for measurement.
So why the distance of 2 of them is smaller?
That's, oh, this one here? Yeah. Oh, that's a glitch in the timestamp.
Okay.
Yeah. It's a short weekend. That's the second explanation. Okay, so lo and behold, over the Christmas period was obviously the best time to measure, and this was then, you can see here nicely the result. Here's the resonance frequency. This is the frequency response of the pendulum, close to the thermal noise limit. Here is here's the force signal. And you see nicely here at the modulation frequency, we see a strong force signal, and we even see the second order peak of due to modulation and nonlinear potential of gravity. And you see the acceleration modulation, as I said, is on the order of 10 to the minus 11 g. But, and the accuracy is on the order of 10%. So this is our systematic error. So we could exclude so 10% of the signal we can definitely contribute to other sources, but 90% we are sure it comes from gravity in that case. And the precision, so really error bound the measurement after 10,000 second average is on the order of 10 to the minus 13 g, so 10 to the minus 12 meter per second square, which is really a great acceleration sensitivity. Okay. So next steps. What are the next steps? Well, next steps, we want to go smaller in mass. No, I mean, there's still a millimeter gold sphere. You will never expect this to be a quantum system. Okay, so next steps is, you see, we want to go smaller, and actually the next thing we are working on is right now this one. This one is a mass on the order of the Planck mass, and we want to now measure the gravitational field generated by a Planck mass. This is what we are setting up at the moment. What's the biggest obstacle? Well, I already showed you what the biggest obstacle is: night buses, trams, and so on. And that is why we have moved the whole experiment to an underground mine tunnel, where we have built it up now. The amazing thing is, I mean, we saw in our lab in Vienna downtown, first of all, we saw everything I showed you, and the whole noise floor was deviating by a factor of 10 during the day. Okay, and this is something we still don't know where that comes from. It's just completely mysterious, just very, very. We put the whole thing here. The background noise was immediately reduced by a factor of 300, and is rock solid 24/7. It doesn't change at all. So we are extremely motivated now, and we see, we think Planck mass is the next feasible thing for gravity measurements. Okay, so. I still have now the second question to discuss. I'm switching gears, and of course I also don't want to take too much of your time. So take a breath, and if there are no questions, I would just continue if this is okay. Yeah? Go ahead.
Is there a limit on when you go down?
Can you repeat?
Before
I will.
you start seeing seismic effects coming from below. Can you repeat the question for them? Oh, okay.
Sorry, is there an estimate or a limit or something about how low you can go before you start getting seismic effects from below, from the inner Earth?
Oh, deep in the ground, you know?
Yes.
Yeah.
Mm-hmm.
Some form.
So you see, the issue with seismic effects is that they strongly depend on frequency. So the seismic effects have like a 1 over f square roll-off typically. So the biggest problem typically is not seismic, but is Newtonian noise. So really background noise, white background noise from gravitational sources that are moving. Clouds then even at some point. Okay, so basically changes in weather conditions that just change the local density and change your local gravity gradient. This is why it's tricky to operate at the super low frequencies. I mean, I was strongly opposing my team when they suggested to build a torsional balance with a millihertz resonance frequency. Okay? And I was actively opposing them. They had a hard time convincing me. Up to this date, I don't know how they convinced me, actually. I'm wondering whether someone just built it and told me. I don't remember, I have to admit. But once it works, you forget about these things. But indeed, we are, because of the fact that the lower you go in frequency, the more dramatic seismic effects become, or other Newtonian noise becomes, the more we are pushing also for higher frequency. So, yes, it will be limiting, but there is a workaround. Okay, simply don't operate at such low frequencies. Okay, now I will make the rest very quick, because the rest now no? Because now I'm talking about quantum physics. I took more time with gravity because people know less about gravity typically, and it's a more fun experiment. So how massive can we make a quantum system will be the next question. Okay? So my team and I started looking in these questions more than 15 years ago now for a completely different reason. I was simply fascinated by the question, can we use the toolbox of quantum optics to manipulate the motion of solid state systems? We know from atomic physics you can use radiation pressure, so the fact that if you absorb and re-emit light you get a momentum kick, you can use that to cool atoms, for example, and to manipulate motional states of atom into the quantum regime. That was the secret key to unlock BC and all cold atom physics these days, all modern atomic physics, so to speak. So could we use those techniques and manipulate solid state systems? Basically like cantilevers, mechanical systems that act upon radiation pressure. And this, along with many other groups around the world during this time, developed into this field of quantum optomechanics, which exploits radiation pressure effects to manipulate the state of motion of solid state systems. So instead of now being able to manipulate the collective motion of, let's say, 5, 10, 15 atoms or ions in an ion trap using quantum optics techniques, you now have methods to manipulate the collective motion of 10 to the 5, 10 to the 10, 10 to the 15 atoms that coordinately move as the center of mass motion of such a solid state object. And I can imagine if I send a single photon now on this cantilever, nothing much will happen. Okay? I mean, it's like a half-line derivation to show that the displacement of a single photon from a typical micromechanical structure that size doesn't do anything. The wave packet just doesn't shift, it decouples. So you need to come up with tricks, and the tricks is strongly motivated by ideas that more or less Vladimir Braginsky already pioneered in the 60s in the context of gravitational wave detectors, that is to have such a moving mechanical element that can move upon radiation pressure, so mass on a spring, and combine it with an optical resonator. So instead of now just having a single photon impinging on a mechanical system, imparting a momentum kick, you have a mirror where the photon is reflected back and forth, and therefore imparts a multitude of momentum kicks. Okay? And this provides you now with a plethora of physics. It's really nice if you just think about it. I assume now that we know about an optical resonator. So it's just a mirror configuration. The distance between the two mirrors is a multiple of the wavelength of the light that comes in. So that means the light is resonantly enhanced inside these two mirrors. Okay. Now, what we also know is if light is reflected from something, then the phase of the reflected light depends on the position of the object that it's reflected from. The basics of interferometry. Now, combine that, what I just said, okay? You send light in here, and then what happens is radiation pressure, okay, pushes this mirror. Right? So light pushes on the mirror, so the mirror moves. Yeah? And the more light you send in, the stronger the mirror moves, which means that the light that comes out of the cavity will have a phase shift that depends on the amount of light you send in, on the intensity. So I put a black box around that now, and what I have is I send light in a black box, and what comes out is light with an intensity-dependent phase shift. If I ask an optics person what is in the black box, the optics person will tell me, oh, it's a Kerr medium. There's a nonlinear crystal in there. Because an intensity-dependent phase shift is a nonlinear optical element. Okay? It's a Kerr medium that can generate non-classical states of light. That's what you use for generating squeeze states of light. So what I have now is just a mechanical structure combined with a cavity provides me with a way to manipulate my state of light. Now that's already very cool, because these things, as you can see here, you don't have to build a cavity with a moving mirror. You can actually have now integrated photonic circuits where light couples to mechanical motion, where photonic cavities in a silicon photonics environment couple to mechanical motion, and you immediately see that you can have now optical nonlinearities encoded by such optomechanical cavities. So you don't have to now build a nonlinear optical crystal inside a silicon photonic circuit, because this is really hard. This is why optical computing did not work in the 80s, because they did not have nonlinear elements to do the switching. Okay? So, and nowadays, so what you could do is now just build such an optomechanical circuit inside a silicon. You can do that all integrated, silicon photonics, and you have your nonlinearities for free. You have on-chip squeezing, and so on and so on. Okay? So there's a whole application platform here now for optical manipulation, just using mechanical interactions. But of course, this goes the other way around. If the cavity is detuned, you know what happens, no? Basically, then light does not enter fully. But if the cavity length changes, more light can enter or less light can enter. But that also means now, you see, if I pump the cavity detuned and my mechanical system changes, then I change the amount of light that kicks it. I change the force on it. So what I have now is, put yourself on the mechanical oscillator. The mechanical oscillator now experiences a force that depends on its position. So that's mechanics 101. I have an harmonic oscillator, and I add to the harmonic oscillator position-dependent force. What does it do? It changes the spring constant. So I have now a way to manipulate the spring constant of my mechanics. And it's a cavity. So that means if my mechanical system moves, then the light inside the cavity doesn't change instantaneously. It's retarded because it's an interferometric effect. It takes some time, the cavity lifetime, to adapt intra-cavity the intensity. So that means I do not only have a position-dependent force, I have a position-dependent force that is retarded in time. Okay, it's a harmonic oscillator. If I retard position in time, I end up in momentum. So not only do I have a position-dependent force, I also have a momentum-dependent force, which means I change the damping. And now I have everything. And so now I have a way, just by optics, to manipulate the full mechanical susceptibility, the real part, the spring constant, and the imaginary part, the damping. That's it. And now, of course, you believe me immediately when I say, okay, this was my classical explanation, but of course, I can say the very same thing in the quantum regime. Now I have a full platform to manipulate light and mechanics in the quantum regime. That's it. I just tried to give you a classical intuition of the whole thing. Okay? From a quantum perspective, of course, the optomechanical coupling is a highly nonlinear one. So you see the cavity intensity couples to the position, and this reflects already the fact that I told you. This is a nonlinear interaction. And if you drive your system more strongly with a laser or a squeeze state, then you can linearize the interaction. And this is something for the quantum optics people among you already know. That's two-mode quantum optics Hamiltonian, a very generic one, XX coupling, and then now depending on how you detune your cavity drive, you can do a rotating wave approximation, and then you have either a co-rotating or counter-rotating term of the XX coupling, which is either a beam splitter operation that generates a cooling or a down conversion interaction that generates entanglement. So we have everything. Okay, this is the whole point about this quantum optomechanics business, that we now have a platform where we can use quantum states of light to manipulate quantum states of mechanics, and vice versa if you want. Okay, so and well, of course, so this just shows you that you can do that with many different systems. You can have a Fabry-Perot cavity with a moving mechanics. You can have dispersive coupling of membranes or particles. You can even have an LC circuit. Okay, where one of the capacitors has a moving end plate. Then instead of having an optical cavity, you have a microwave cavity. And you can do everything I just told you in a microwave regime. And finally, now for the atomic physics people here among you, this has also a very nice representation in a scattering picture, a photon scattering picture. So if this is your optomechanical system, and in the frequency domain, you see this is your cavity frequency, okay, here. Right? And you see, if you now pump your cavity blue detuned, what happens is, in order to scatter a photon in the cavity, you need to get rid of some energy. If you detune by the mechanical frequency here, you see the way to get rid of the energy is to create a phonon in the system. That's a Stokes scattering process. It's a Raman scattering process, and the Stokes scattering creates a phonon. And obviously, if you red detune, then the only way to scatter a photon into the cavity is to extract some energy, so get some additional energy from the mechanical system. So you extract a phonon, and of course, if the photon, this is now an anti-Stokes scattered photon inside the cavity, leaks out of the cavity, it carries away the energy from the mechanical system, and this is what's called laser cooling. So this is how you can now cool the center of mass motion of the particle until you reach the quantum ground state. And all of this, I mean, now we can, this picture of resonantly enhanced anti-Stokes scattering is, of course, exactly the picture that Dave Weinland and others invented for sideband cooling of ions in the atomic physics community. It's exactly the same physics. It's just that here we use the cavity to mimic our two-level system. Okay, I'm really going over time here, so let me wrap this part up. So here's just an example of what we did back then. I told you, so this is why I was here, our 2006 paper, very old 2006 paper, where we showed for the first time that we can use radiation pressure to really cool the center of mass motion. And the idea is really, in that case, you see, you just have a cantilever here made just out of optical coating. And you make that as part of a Fabry-Perot cavity, and you can see even here, you see on the cantilever, this is the cavity mode that comes from above, is reflected, and then you just change the cavity length, you detune the cavity, and in that way you can enhance the anti-Stokes scattering process and you extract energy. And back then we went from room temperature to 30 Kelvin or so in phonon occupations, only a factor of 10, because the heating rates were so large. The cooling rate was okay. Even if you have a very small cooling rate, if there's no reheating, you cool to the ground state eventually. But the problem is, of course, the mechanical quality was very bad, and so that means there was a lot of reheating, many phonons getting back onto the structure, and so we never went to the ground state. And so the next years, we had to engineer our mechanical structures in a way that less and less phonons would leak back. So this was really a mechanical engineering challenge to get to mechanical structures that were of sufficient high quality and at the same time of sufficient high optical quality to sustain the laser cooling process. And eventually, then in a collaboration with Oskar Painter, He was the one who pioneered this new optomechanical structures, photonic crystals. If you want more, I will go into the details, that eventually allowed us to cool down to the ground state. And then we thought, oh, that's super. This was an experiment we did at 4 Kelvin. We showed ground state cooling at a 4 Kelvin temperature. We thought, oh, we have a dilution fridge in the lab. We just take the experiment, put it in the dilution fridge, and then we should go from here to here. Just because the base temperature is smaller. So we did it, and we got this data point, you see almost the same, and it took us another 4 years to really work out how to operate an optics experiment in a dilution refrigerator. So this is a completely different world. Ever since then, in my group, we consider a 4 Kelvin experiment a room temperature experiment because it's so simple. Okay, so I apologize for this very long story. But I just wanted to convey a little bit the whole developments that now led over the last 15 years really to a situation where from conjecturing we should be able to control mechanical systems in the quantum regime, now in a situation where all around the world we have many labs that can reliably and in an incredibly great way control mechanical systems in the quantum regime. So from ground state cooling, generating non-classical states like squeeze states, generating non-Gaussian states, generating entangled states, and so on and so on. So this is really now state of the art everywhere around the world, and has led also to many ideas and applications. Of course, there's this whole application world of gravitational wave detection. If you see gravitational wave detectors now operate as a standard with squeezed light input, but in order to make an effect, what they exploit is radiation pressure effects inside the cavity that then create out of the squeezed light input measurement sensitivity below the standard quantum limit. So it requires optomechanical effects inside the gravitational wave detectors. Then there are brilliant ideas by people like Oscar Painter and others about photon-phonon microcircuits. Microwave to optics conversion is a big topic also for the quantum computing community, and again, because of this nonlinearity I told you about, it's actually the transduction between microwave and optics domain via mechanics is an extremely promising approach. Same for sensing. There is a whole scope of ideas. This is something we can also talk tomorrow about. And also what I said before, on-chip signal processing doesn't even require mechanical quantum states, but it uses this optomechanical interaction. So, I will wrap it up, okay? So I come back now to this part. Because now I think what I wanted to motivate is that we have everything in place. No? We do have, we have a path towards isolating gravity for smaller and smaller masses. And we have ideas how to manipulate solid-state systems in a quantum regime. And why is this so important? Because you need many, many atoms in a small amount of space to create a sufficiently large mass and hence sufficiently large gravitational field to mediate the coupling. If you go to non-solid state densities, there's no way that coupling rates would ever be in a regime of experimental feasibility. You need solid state densities. But now you see the problem, okay? The problem is for small masses, like the meta wave experiments I showed you, you have super long coherence times. And super long coherence times you need because this is the time scale at the end of the coupling that you can afford. Right? But you see right now the solid state experiments, they increase the mass. It's a log scale. No? You go from 10 to the 3 atoms to 10 to the 10 atoms. This is a lot. No? 7 orders of magnitude is nice, but you also reduce the coherence time by 7 orders of magnitude, or even 9 in some cases. So the challenge is now, can we get a quantum experiment to operate somewhere here? Okay? Large coherence times and large mass. This is the actual challenge. And this is where this idea here comes in. So we know that the large mass is provided by the solids, the clamped devices, super large masses. We know that the meta wave community with their free fall experiments, because the atoms just don't interact with anything. They're freely floating in vacuum, live happily ever after. And this is why they have these long coherence times. And what we want to do now is we want to combine these two ideas. Okay? So take a solid and detach it from its environment. How? By levitating. Okay? That's the whole idea. Take it, levitate it, and levitation is nice because you can use an external trap to keep it, but then you can also switch the trap off. You can manipulate the trap. You can make from a monic potential, you can go to a anharmonic potential, even a repulsive potential. You can do everything. You can do all the stuff that we were talking today with Luigi, that the atomtronics community is like really harvesting of. They are the ones who have developed already all the techniques to shape their wave packets. And now we want to shape our wave packets, but it's a single particle wave packet of a massive solid state center of mass degree of freedom. That's the difference. Okay. Now I really should come to an end. Okay, so I know we started late, but I give you a glimpse and then we stop. Here's the glimpse. So we have a couple of different ways to levitate. Here's one possibility. You just take an optical tweezer. Optical tweezer is something that the world knows. You have a dielectric particle. That in our case is like here, like 150 nanometers in size. It's dielectric, that means it's polarizable. That means if it sees an electric field, you induce a dipole moment. So the overall coupling with an electric field is dipole moment times the E field. Since it's an induced dipole, this dipole is just the polarizability times the E field. And so the overall energy landscape that the particle sees is simply given by E squared, which is, if this is a light field, just the intensity of the laser light. So this is why you see the intensity of the laser light provides you with the potential landscape of the particle. So that means if I have now a Gaussian laser beam with this intensity profile, then the potential landscape is just the inverted of that. And you see for small displacements, the Gaussian just then looks like an harmonic potential. So for small displacements, I now have a 3D harmonic confinement of the particle, and that's what's called an optical tweezer. And this is, of course, now great, because I can trap now the particle, you see here, right in front of a microscope objective, and it's nicely harmonically trapped. And then you add a couple of experimental, let's say, gadgets. For example, so you see now here again, this is our microscope objective where we keep the particle. The laser light focuses it, traps it, and then you see the light that is scattered in forward direction. We just keep, we measure it, and this provides us with X, Y, Z information that we use to stabilize the particle position, and so you can keep it at very low pressures. And this is actually also beautiful work that René has done in his Zurich times, where he has also been working on exactly these types of stabilization and measuring of these particles for quantum controlling them. And now what you can also do is, you see in our case, what we did is we collected the backscattered light, because that carries a lot of information about the position, and we used that to measure it with such a precision that we could monitor the particle trajectory with a precision of the ground state extension of the particle. Okay? So basically what we did was, with this backplane imaging, which is a method from microscopy, we actually had a sensitivity at the Heisenberg limit, close to the Heisenberg limit. So we could monitor now the particle motion close to its ground state, which means we can basically in real time follow the quantum trajectory of the particle. And now if you apply a so-called Kalman filter, which just means you have a good state space model of your system.
What kind of time resolution you need?
This is a 100 kilohertz system. Okay, so that means somewhere if you're in a 10 microsecond regime, it's fine, or 1 microsecond if you're oversampled by 10. Okay, so that's super simple. And there was still a cheap FPGA where we encoded this whole thing. We now got a better one because we want to do more advanced protocols, but this one was still a simple one. And you see, using the Kalman filter, you can also now do state retrodiction and prediction, which means you can also stabilize now the state of the particle with a precision of the ground state, which means if you stabilize it, you ground state cool. Yeah, that's called ground state cooling via feedback. And what you see here is actually a picture of the particle ground state cooled in a room temperature environment. Okay, so this is a real picture, yes?
What is Kalman filtering?
So Kalman filtering is simply, the Kalman filter is a state space model. If you want, from a quantum perspective, it's simply a stochastic Schrödinger equation where all of the relevant noise terms of your system are taken into account. That's it. And Kalman was the first one to come up with it, with basically the ability to have full state description via stochastic differential equations and apply then feedback. And Belavkin in the 80s, I think, was the one to realize that if you want to do a full quantum state prediction of Gaussian states, it is sufficient to have a classical Kalman filter where the noise term is then just quantum noise. Okay, so here's an example then how you do feedback to cool. Then let me give you one example there that includes also René's latest, greatest contributions. This was something that we did back to back between Vienna and Zurich. And in Vienna it was Uroš Stelic who was the driving force, and in Zurich it was René who was the driving force. And I think it's fair to say this was a very nice collaborative effort then to have a really beautiful experimental demonstration of something that was also only known to the atomic community at first. And in the end, you know it already, so I just give you everything in a nutshell. We have the particle in the tweezer, and of course, you know, the particle moves, so the tweezer light is also scattered off the particle. And you will also have, again, Raman contributions. We'll have Stokes and anti-Stokes scattered photons. Okay? So if you put now here a cavity, an empty cavity, okay, just two mirrors that are put in such a way that they now on resonance with the anti-Stokes scattered photon frequency, then only those photons will be scattered into the cavity that take away energy from this motion along the cavity axis of the particle. And just the presence of the cavity is now like a fridge at 0 temperature that cools the particle motion in the quantum ground state. And these are the two works then that demonstrated, that showed the theory, and then we did the experiment that basically just shows what I said. So we put the cavity around the particle and then demonstrated cooling to the ground state. Similar occupation than in the other case, and also again in a room temperature environment. The interesting part of the cavity is that in principle one can reach extremely low occupations. So this is something one to take into account. Okay, so now I'm wrapping up. What are the next steps? Now we have a particle wave packet prepared in its ground state. So this is now basically, we are more or less where atomic physics was like 50 years ago, no? Yeah, more or less. We do have now, we claim we can prepare pure state wave packets of the center of mass degree of freedom of such a solid state particle. One of the next steps is, can we prepare a large wave packet? So couldn't we now do a wave packet that is larger than the size of the object? Why? Simply because it's cool. So there's still no practical relevance other than now we are very sensitive to external influences. Yeah? And so, for example, if you would switch off the trap, the wave packet size would already, on a 10 millisecond timescale, expand from 3 picometer to the scale of the particle size. Yeah? So this is something that is not totally impossible. But then, of course, if you put the numbers, I spare you with the details for reasons of time now. I just tell you that decoherence is, of course, a killer for these large systems. So what you really need is you need to avoid gas collisions. So you need to operate at very low pressures. And you need to avoid blackbody radiation. Blackbody radiation is really, really bad. And this is why also the environment will have to be cryogenic. And this is the challenge. Okay, so for the next upcoming years, the challenge is having a pure state wave packet like that, how can we generate large superposition states? There are several ideas out there. We have published a couple of theory proposals in the past. Here is one together with Oriol Merezar to do that in post-selection, like a conditional state preparation. Oriol had a beautiful proposal how to do that via coupling, for example, to some nonlinearities like a superconducting qubit. And there are also alternative ideas using internal degrees of freedom, like in the spirit of Feynman, so doing a Stern-Gerlach type experiment, where you then separate the wave packet. Who knows? Yeah, and this is all part now. So this question is something that we are investigating together with the groups of Lucas Novotny, Romain Quidon, and Oriol Romerizat in the context of a synergy grant. So this will keep us busy. And one of our approaches is, well, why not shaping the potential landscape? This is something, again, we already had this example of atomtronics. This is exactly what the power is, that you manipulate optical potential landscapes where the atoms now live in. And this is also something that we are doing right now, as Mario Ciampini and the group of Nikolai Kiesel, with whom we collaborate strongly, who has now mastered using some spatial light modulators and other techniques to change the intensity profile within which the particle is trapped. And you see, when you go, for example, from a Gaussian to a, let's say, just a TM01 mode, okay, then you already see that the TM01 is something like a repulsive potential, and everything in between is something else, a double well, a cubic. Yeah, you can do everything like that. And this is the type of experiments that Mario is following at the moment, and we think we can nicely adapt that to our needs. Good. So I conclude. I showed you that we have different approaches here to, and I wanted to sort of motivate why we are interested in the question how small can we make a source mass and how large can we make a quantum system. And eventually, somewhere hopefully in the future, come into a regime, experimental regime, where these two actively coincide. So we have on the one side, we have now these gravitational measurements of millimeter-sized particles, and we hope to push that now down to the Planck mass regime and hopefully below that. And at the same time, now we need to come up with methods. Here's our cavity with the particle to, from the ground state to really go to larger superpositions and then to crank up the mass also. Right? So we also need more massive systems, and then I hope that somewhere, someday, they will meet. Good. I leave it like that. There are still, of course, many, many more details. If you're interested, I'm happy to share, and I just leave it like that at the moment. Thanks a lot.
Thank you very much, Markus, for such a great talk, and congratulations on the amazing physics that you guys have been doing. This is really, really, really cool. And thank you for the nice introduction. This was very self-contained.
Thanks.
Great. So this has been a long session, but we do have time for a couple of questions, which I am sure there are some questions over there. So as usual, I start with the students and the junior ones.
So. To the question of how small you can make a system and how big a quantum system can be, are there no theoretical limitations to that, or is it a purely experimental setup and pushing the boundaries of what we can control thing?
Mm-hmm. Mm-hmm. So this is an open question. Based on our knowledge about nature to date, so if I take the theories that we have, there should not be a fundamental limit to the quantum character of solid state degree of freedom. Quantum physics doesn't care about the object, it only cares about the degree of freedom, the center of mass degree of freedom, and I should be able to, so there is no fundamental limit. And the same from the gravity side. From the theories that exist today, from our current knowledge of nature, there's no fundamental obstacle, just practical limitations. Of course, there are people who believe that quantum mechanics breaks down at some point, either due to gravitational coupling or due to so some people would expect something to happen in our attempt to do these experiments, but this is new physics. So I mean, if there would be something, it would be new physics. That's what I mean. Yeah. Not what we are doing. What we are doing is old physics.
So yeah, just to extend that a little bit, I guess, the issue of measurement, breaking down superpositions and quantum states when you go to large enough systems? Is it just a matter of having everything be extremely isolated? Are there sorts of spurious measurements that might break things down?
Yes. So I think it's exactly what you said. And again, I'm saying, given the current state of knowledge about quantum physics, it's really just a matter of isolation. And the problem is, of course, the larger the system, then the more problematic will be any sort of influence. I mean, even a single gas molecule just localizes the thing. If there should be something like dark matter, okay, and let's say if by any chance the dark matter happens to be in an energy regime that there is some, I don't know, inelastic scattering possible from our large systems, it will decohere it. So maybe we will confirm that quantum physics is right, and we will then by accident identify dark matter. No idea. Yeah. But this is the, and I think this is the real challenge then in the long term. If you do the experiment, and then obviously it will never be perfect. Okay, and there's a good chance that you do the experiment and you expect to see some interference and you just don't. Will you, after your first attempt, will you immediately conclude, oh my God, quantum physics breaks down? No, you will start to hunt down possible effects where information is carried away. So natural decoherence. So this is a interesting process.
Thank you.
Any other question do we have?
Hi, I actually have two questions, but I'm going to start from the optical tweezer experiment. I was more familiar with the experiment of optical tweezers in the context of electromagnetism and biology. And there usually the nanoparticles are in a liquid, and the lasers are fixed, so you move the liquid in order to trap a nanoparticle. So how are you able to isolate without a liquid medium just one nanoparticle in that optical tweezer in the air? If you do that, how do we avoid other particles interacting?
Yes.
So that's my first question. And then I have another.
And the second?
The second is about what Luigi asked before, like if and when we can converge the mass and the quantum system to the regime that you want, how do you describe the experiment with a theory? I would like for you to expand on that.
Okay. So I make that quick. First question is an excellent one, right? And René and I could tell you hours of stories about how to isolate such particles. Here's the lame starting story is you go to a pharmacy, you buy an asthma spray nebulizer, you know, the thing, and then you go to a homeopathy person that teaches you how to dilute something in a solution, okay? And then you prepare a highly diluted solution with particles. You fill it in the asthma spray. You open your vacuum chamber. You switch on the laser first. Then you spray inside, okay? And because you want to do a cavity experiment, you remove the cavity, and then you wait. Because it's highly diluted, it takes like 10 minutes to 30 minutes until you catch a particle. Okay, and you can be sure it's one because the solution is highly diluted. And at some point you already learned how much you have to dilute it in order to just have one, So it's as like a Poissonian distribution of particle number per bubble, and then you pump down to basically get rid of the liquid, because the particle then heats up, the liquid is gone. Then you let some dry nitrogen in again. Okay, then you open the chamber again, the particle is still trapped. Then by hand you put in the cavity. Okay, you close the vacuum chamber and then you pump down again, then do the experiment. No choking. So this was how initially these experiments were done. And so you see there's a desperate need of improving the methods. And right now there are a couple of methods. One is particles are on a piezo and are basically just shaken off. This is non-trivial because for these super small particles, van der Waals is very strong, so you need to come up with methods how to either passivate the surface or add, somehow assist the binding by some laser or heating. And what we are doing at the moment, it's also a 8-year project now already, but we are so now it's working now, so close. We have a hollow core fiber. You know what a photonic crystal hollow core fiber is? It's basically, you need an index jump for guiding light in an optical fiber, and you can also do that by having air in the inside and having a photonic crystal structure in the outside. That's something Philip Russell and others pioneered a long time ago. And what you can have now is you can guide light through this fiber, which is hollow, but it also means you can have particles that go through. So we do something that in Mesched's group was developed, a so-called optical conveyor belt. You have a standing wave with light. You place a particle in front of the fiber, and this you do with the spraying approach. But the point is now, you can guide now the particle through the fiber, and the fiber is so small and the air gap is so little, the diameter, that you can connect two vacuum chambers with it, and it can sustain a pressure difference of 6 to 8 orders of magnitude. So I can have a chamber here at a millibar connected with a hollow core fiber that sits at 10 to the minus 9, 10 to the minus 10 millibar. Okay, and that means I now have a deterministic dry loading scheme where I can deliver individual particles then to my experiment. So second question. Well, at the end of the day, the most simple description of this experiment, I'm really sorry to say that, is actually the one that I showed you here. This is the most lame way of describing it, because really in a tabletop experiment of first order, that is what's happening. Although of course the modern ideas, so what's really going on. So this is the transparency I didn't show you. There are two possible ways of generating entanglement, okay, between the two. The one is, where's my mouse? The one is you simply have two harmonic oscillators, okay, that are separated by a distance, and you just couple them via a Newtonian potential. And this just generates Gaussian entanglement. Even if actually the entanglement rate, you can compute that as like a one-line derivation, scales with the size of the wave packets. Okay? And the other way of doing it is, more in the Feynman spirit, you have one particle in a superposition, the other particle in a superposition, and you see now this particle here lives now in the superposed metric of this particle. Okay? So this is now similar to the cow experiment that I showed you. So this particle experiences a phase shift because of the potential generated here. And now this is a conditional phase shift, because depending on where this is, okay, and now what you have is now a C sine gate, quantum information wise, okay. It's a C sine gate with two 0 plus 1 input and control qubits. And this is an entangling gate then. And interestingly, you see the entanglement rate, you can compute that for these both cases. The entanglement rate is the same for both.
That's fantastic. Professor Aspelmeyer will be here tomorrow also, so there will be plenty of time for further discussions. It's already more than 5:30, so I think that we can call it a day for Professor Aspelmeyer, and thank you so much again. Let's clap hands again for the speaker.